Now in this video I will show you how you can use a transistor as a switch to trigger a light-emitting diode, an LED. Firstly, there's going to be a short review of the transistor as a component and also of its input characteristic curves, and then we will quickly look at the most important formulas for finding the resistor in order to protect the LED from too much current, and then we're going to conduct a small experiment using Tinkercad as a simulation tool. And as always, if you have any questions, just drop them down into the comment section and I will try to help you as best I can. And now enjoy the video. If you have seen the last video, you might already know the transistor as a very important component in electronics, and you might have already seen that designing a circuit using this component is rather simple and straightforward, and you can use Ohm's law and Kirchhoff's laws to dimension the surrounding circuitry in order to operate the transistor as a switch. And now it's time to put this theory into practice and to build and test the circuit. And firstly, as the first part of this video, we're going to quickly review some of the most important theory items which we need in order to operate the transistor as a switch, and then we're going to construct and test the circuit. And let's go now. Now firstly, our goal is to make the transistor fully conductive, and in order to do this we're going to use a carefully targeted base current which leads to a current flow through the collector, and this will make the LED light up. Here's the basic circuit which we have discussed previously. We have a supply voltage UB, we have a resistor which protects the LED from too much current. Here's the actual LED which we want to switch on and off. Here's the transistor, collector, base, emitter. Here's the base resistor which controls the amount of current flow into the base, and here's the signal voltage which generates this current flow into the base. And what we want to achieve is we want to get to a current flow of 20 milliamps which should flow through this LED here. And in order to enable this switching operation, we need to operate the transistor in the saturation range, which is this magenta colored part here. On the x-axis we have the current, the voltage drop from collector to emitter, UCE, and here's the collector current amount in milliamps. And in order to get to a decent amount of collector current, 20 milliamps, this would be this would be here. We need to, as you can see, we need to choose a very small collector emitter current. In order to get to our 20 milliamps, we can look it up on the data manual for a certain type of resistor, for example the BC547B, which we have done in the previous video, and this brings us to an operating voltage of 0.02 volts, which need to drop across these two connector here, collector emitter, in order to generate this current flow. And this can be retrieved from the data sheet of any resistor in case you want to use a different one. Now let's look at the simulation of the circuit here. We have the transistor, we have the LED, we have the resistor protecting the LED. Let's enter these values here: 344 ohms for the LED resistor, 186.3 kilo ohms for the base resistor, and the current flow which we observe here is 20 milliamps, so a little bit more. And in case you are wondering where we got the values for the resistors, we have been using these formulas here, and how they can be derived has been a part of the last video. And what I want to do now is I want to construct the same circuit here in an actual laboratory setup. So let's head over there. Let's take a look at the circuit as we have seen it before in the simulation. The heart of everything is the transistor, which you can see here. If you take a very close look, it's hard to see in the light, but if you take a very close look on the housing, it says BC547B. Also, there's a small e in the lower right corner here, and this tells us which data sheet to fetch in order to extract the parameters from. And also the small e tells us that this side here, the right bottom side, is the emitter of the transistor. In the middle, as always, is the base of the transistor, and the upper connector here, this is the collector of the transistor. And let's take a look at the circuits here just for a sec. On the collector we have the resistor which leads to the LED, and this is the resistor which protects the LED against too much current. If we pull it out, this side here is the positive lead. This has to be connected to the positive terminal of the battery, which is going to be connected to this power rail here. And the other side, this is the cathode. This is connected to the resistor. And we have made a video on how to use a breadboard before. And by pushing the connector, the cathode of the LED into this column here, we ensure that it's connected to this side of the resistor. So let's follow the path of the current for just a sec. Let's connect the battery. The battery is going to be connected to the upper power rail, this one here. Then the current flows into the LED, it comes out the other side, flows through the breadboard matrix into the resistor, comes out the other side, flows into the collector of the transistor. Then inside the transistor, we have the base, which is connected to this resistor here, which we have computed to a value of 186 ohms, I think. However, in my box, I only had a transistor, a resistor of 180k, which is close enough to make this circuit work as we intended to do. Also, maybe just for your information, the resistor here is not, the resistor protecting the LED is not 344 ohms, it's only 330 ohms, but this is also good enough to protect the LED here properly. Now, when we connect this side of the resistor to a signal, then if the signal is high enough in terms of voltage, the base is going to be at a sufficiently high potential to open through the, or to connect the collector to the emitter. Then the transistor, as we designed it to be, is operating in its saturation mode, which means the connection between collector and emitter is ideally conductive regarding the parameters of this transistor here. And this means we have a current of approximately 20 milliamps flowing through the collector emitter path, through the resistor here, through the LED, and into the terminal of the battery. And the emitter side here is connected directly to the negative terminal of the battery, which is not yet connected to the breadboard, but which I just added here. And now the circuit is closed, even though you can't observe anything happening with the LED just yet. But now we have a fully operational circuit, which is only missing the right signal to start the experiment. And this signal is going to come from this yellow cable here. And if we connect this yellow cable to one side of the resistor leading to the base and the other side to the battery voltage, then as we designed the circuit to be, the voltage is sufficiently high, generating a sufficiently high base current to make the transistor conductive, which you can see now as soon as we connect it to this power rail here, to the positive power rail. Now the transistor is fully conductive, and as expected, the LED is glowing in a bright light, indicating a sufficiently high enough current, just as we designed it to be. We won't take a measurement now, but the brightness suggests that the LED is getting at least 20 milliamps of current, and this is just what we intended it to be. So now we have a transistor in use as a switch, driven or triggered by a voltage signal, and in one of the next videos we will generate a voltage signal by using an operational amplifier which is connected to a light sensor. So eventually in the final stage, this is going to be the stage which is triggered by the light sensor, and as soon as the light intensity falls below a certain threshold, there will be a signal connected to this cable here, and this will bring the LED to glow. But that's a topic for one of the next videos. For now, we have seen how to use a transistor as a simple electronic switch.